Hey, how you doing? I wanted to reach out and talk about the Hardy Weinberg principle, not to be confused with Harvey Weinstein. He's not a nice person. But Hardy Weinberg were two people, and they came up with a mathematical equation to look at the frequency of alleles within a population. And the extra credit assignment that goes along with today's classwork deals with that. So it's on page 491 in your textbook. It's the analyzing data right here. And so we want to look at the stuff that's here. So we're asked to calculate the frequencies of the big S and little s alleles. We're asked to calculate the frequencies of the big S, homozygous dominant, big S, heterozygous, and little s, homozygous recessive genotypes. These are the genes that they actually have. And then they want to know what percentage of people in total is likely to be carrying that little s allele, whether they know it or not. And so we need to know then the frequency of the homozygous recessive and this heterozygous, because these individuals that are heterozygous are going to carry the allele, not know it because it's recessive and they have a dominant allele to go with it. And so we need to do that. Hardy Weinberg they came up with these two great equations that together are known as the Hardy-Weinberg principle. And it says that P plus Q equals 1. Now realize we're dealing with percentages. We're dealing with frequencies. And so 1 is 100%, just like 0.5 is 50%. And you hopefully are comfortable making those percentage conversions. They're not hard. You just shift your decimal 2 places to the left. So 1, 2 places to the right, I'm sorry. Moving your decimal from 1.0 over 2 places would give you 100. 2 more zeros. The P is always going to be our dominant allele. The Q is always going to be our recessive allele. And I'll make note of that in a second. And so the second part of the Hardy-Weinberg principle looks at the frequency of those alleles as far as genotype goes. This specifically looks at phenotype. And so we've got P squared plus 2PQ plus Q squared equals 1, or 100%. So anytime you have these Hardy-Weinberg problems, you need to use sort of both of these equations together. Generally what happens is you're given the frequency of one allele, typically the recessive homozygous, because they're the ones that show up and they're the easier number to count because it's a smaller number, typically. And so first thing you do is you use that in this first equation to figure out your dominant allele frequency. And then once you know P and Q, you just plug them into this bottom equation and you can solve for whatever you need. So it's actually, it seems hard, but it's actually pretty simple. So let's mark this up a little bit, I guess, just so we get some notes. We'll use red. No, we'll use green. So the P is going to be dominant. Oh, I did the background color, so we'll just swap them. Okay. Cancel. There we go. Now we can get our green. Fair enough. And now we can erase our mistake. So, like I was saying, P is our dominant. And Q is going to be recessive. And we see that down here. as well. This is homozygous. And I'll try to remember to write slower. This is homozygous. This is recessive. And this is dominant. And then here we have our heterozygous. Okay. Homozygous means they have only that allele. So if they're homozygous dominant, they only have the dominant allele, that big S in the case of our example. If they're homozygous recessive, they only have that recessive allele, the little s, in the case of our example. And for the heterozygous in the middle, they have one of each. They have one dominant and one recessive. Okay. And so I don't even know if it's worth writing down here. P is going to be big S. Q is going to be little s. I don't like using s's when I'm doing genetic work with these dominant and recessive things, because you can't really tell a big S and a little s apart other than their shape. So let's take a look at the actual problem, the equation, and I'll sort of walk you through that a little bit. I'm not going to solve it for you, but I will walk you through it. Let me get rid of some of these notes first so I can get my equation saved and have some workspace. Erasing takes a while. So what we'll do is we're just going to grab this. And we'll transform that and make it smaller. So we can keep our equations and still have space to write. So if we look at this, we see that we've got a population. Let's turn this back on here for a minute. What are we given in the problem? So we're told that there's a condition that only affects homozygous recessive individuals, so people that have little s, okay? The heterozygous phenotype shows no symptoms. So if they have big S, little s, here, they don't show symptoms of the disease, okay? Population you're studying has a size of 10,000. There are 36 individuals affected by the condition, meaning there are 36 individuals out of 10,000 that have that little s genotype. Okay. And so mathematically that works out to 36 out of 10,000 is 36 10,000ths. So our Q squared is going to be 0.0036. Okay. Based on this information, we use the Hardy-Weinberg equations to answer the following questions. We already talked about the questions. What are the frequencies of the S and S alleles? What are the frequencies of the dominant homozygous, recessive homozygous, and that heterozygous? Okay, and then what percentage of people is in total is likely to be carrying the S allele? So we need to find this and this frequency together. And this is a really standard presentation of this problem. So the first thing we need to do is we know that, let's get black again. Doo-doo-doo. Um, 0, 0, 3, 6. So let me show you what I wrote down here. So our q squared equals 0.0036. And maybe you can't see my decimal good. It's better. Not much. And so the first thing we need to do, we can calculate that s because we know that p plus q equals 1. So if we know q squared, the square root of q is going to give us that. And then we can do the square root of q squared, right? And subtract that from 1. Because we're going to move that to the other side of the equation. This will be 1 minus square root of q squared is going to equal p. Once we know that, we can take p and plug it into this equation, just square it and do p squared. We already know q squared is 0.0036. And then once we know PQ, we can add them in there and see if it all sort of adds up. And so it shouldn't be super hard. But this is that key, that 1 minus the square root of q squared. That's going to give us our p-value. And then once you have that, it really is pretty simple to just sort of plug it in and figure it out. I'm going to leave it there because it is extra credit, so I don't want to solve it for you. Good luck and stay healthy. And you can turn this in, you know, you don't necessarily have to turn it in with the homework. If you want to turn it in a little bit later, that's fine separately. Okay. And it is extra credit, so it's not required. All right. Be good, stay safe and healthy. Bye-bye.